The title is Koopman Representation of Positive Definite Functions and Bounded Corput Sets. Please.
Thank you for the introduction, Jonathan, and thank you all for coming here and giving me the opportunity to speak. So the plan for the talk is as follows. I first want to just review some statements, so what we already know about representations of positive definite sequences, as well as two of the new results that I proved. And then I want to review the Gaussian measure space construction, because that's used in these previous results. And after that, what improvements we can make when we work with the special class of abelian groups. And lastly, I want to show how all of this ties into the study of van der Corput sets and sets of recurrence. So first, never hurts to review just the definition of positive definite. So if we have a locally compact second countable group, which is the most general situation that I will be working in, and then we have a complex valued function on the group, this function is going to be positive definite if for any finite collection of complex numbers and any finite collection of group elements, this sum is non-negative. And we denote the set of all continuous positive definite functions on our group by bold P of G. And for a guy like me, I usually don't use this definition of positive definite. I always work with this latter definition, or I guess it's really a theorem that ends up being the same. But a good while ago, Gelfand and Raikov showed that if you're given a continuous positive definite sequence on a group, then there exists a unitary representation of the group on some Hilbert space, and the cyclic vector for this representation, such that the values of your positive definite function, phi of g, are realized as an inner product of UGF with F.
Does you need to be continuous in this theorem?
Yeah, so for me, when I say representation of a group, I'm assuming that it's a strongly continuous map into the group of unitary operators on the Hilbert space. So in particular, that's why I'm also assuming that the positive definite function is continuous in order to make this happen. Although, just as a side note, any measurable positive definite function is going to be almost everywhere equal to a continuous one. So assuming that it's continuous is a very mild assumption. Now, one way in which this previous theorem can be improved is through the use of something called the Gaussian measure space construction, which we'll briefly review in a few slides later on. And basically, using this Gaussian measure space construction, rather than just working with some abstract Hilbert space H and some abstract unitary representation U, we can assume that the Hilbert space is L2 of a measure-preserving system, and U is a Koopman operator of some measure-preserving action. Now, I want to improve this further. So here's one of the two ways in which I'm going to improve the previous result. We take a locally compact second countable group and a continuous positive definite function. And now, rather than just making some measure-preserving system, I can create an ergodic measure-preserving system and then a function f in L2 such that the values phi g of our positive definite function are these inner products of TGF with F. And of course, TG is the Koopman operator induced by the measure-preserving transformation.
Sorry, Mr. Does it need to be finite measure or?
Yes, for me, when I say measure-preserving system, it's always a probability measure on the space. And then if we assume that our positive definite function is real valued, the function f we take here can also be taken to be real valued. And this, it is somewhat of a small point, but hopefully it'll be clear why I care about this later on when we get to van der Corput sets and sets of recurrence. So again, the main improvement of this theorem over what we get from the Gaussian measure space construction is the fact that our measure preserving system is ergodic, and we'll revisit this point when I review the Gaussian measure space construction. Now, other than ergodicity, I want to make a different type of improvement. And unfortunately for this other improvement, I can't get the full generality of locally compact second countable groups. I have to assume that my group is abelian. And then in the case that the group is abelian, it's conventional to think of positive definite functions, which are normalized to have phi of 0 equal 1, to be associated with a measure on the dual group, because we can always, I view our positive definite function as Fourier coefficients of a probability measure on the dual group. So I'm gonna switch to this point of view just because it's more conventional in this situation. So now, assume that we have a countably infinite abelian group and a probability measure on the dual. Then there exists a measure preserving system and a function in L2 such that the value of each point has norm 1, and the integral of this function gives us the point mass at 0, and then the correlations give us the Fourier coefficients.
Can you compare this to Hilbert? Do you know, are you familiar with this classical result by Hilbert?
Yes. So Herglotz, the key difference between this and Herglotz is that Herglotz does not give you a measure preserving transformation. Herglotz just gives you a unitary action of the group, and then some measure on the dual group, such that when you apply the unitary operator to the constant 1 function, you start getting characters on the dual group. And then if you take the inner product of 2 characters with respect to this measure, you get these Fourier coefficients. So it is very similar to Herglotz, but this time the change is that it's an actual measure preserving system rather than just unitary action. And one thing you might notice is that here I just said measure preserving system and not ergodic like we had before. So we can actually see that this construction is almost never going to be ergodic. If the measure preserving system here was ergodic, this integral would be the square root of the point mass. But it's not the square root, it's just the original point mass. So there is no chance that it'll be ergodic unless the point mass is 0 or 1. And even then, there are some examples when it's still not ergodic. So this construction is very non-ergodic. And of course, we can modify this construction to say that if our positive definite function is real valued, then we can take our function to be real valued as well. But now it's not going to have pointwise norm equal to 1, because that would just be using the values 1 and -1. Instead, it's going to be a bounded function, and specifically the points are going to be bounded between -√2 and √2. I don't know if you can do some other construction to assume that f prime only takes the values 1 and -1. That's going to be related to some open problems at the end. So we'll revisit that in a moment. So now, of course, one question you might be wondering in light of these 2 theorems is if it's possible to get both of them simultaneously. Say in the case of an abelian group, can we get ergodicity and a function whose points have norm 1? Unfortunately, no, we cannot get both of them at the same time.
Sorry. So on the last line, integral x of f or f prime.
Oh, I'm sorry, that should be f prime.
Aha.
That's correct. That's a typo, thanks for pointing that out.
But I don't follow why this furthermore is, let's say, important. What's the point here?
Can I defer it until section 4?
Yes.
Okay, thank you. So in order to explain this result that says I can't take both of the previous theorems at once, I can't get ergodicity and boundedness, we just need to review some definitions. So subset of the 0, 1 interval is symmetric if E is equal to 1 minus E, and it is a Kronecker set if for any continuous map from E into the unit circle, there is a sequence of integers such that your function can be approximated uniformly by exponential functions along ns, along the sequence of integers. Right, so normally if we use Stone-Weierstrass or something, we know that any continuous function can be approximated by finite linear combinations of exponentials. But the Kronecker set is saying that I want the continuous functions not to be approximated by finite combinations, but just directly by the exponentials themselves. And you can make an example of a Cantor set that is a Kronecker set, and it's not particularly difficult. This nice book of Kornfeld, Bowman, and Sinai has a nice construction of this at the end, very readable in case you're interested. Now, there's this classical result of Foias and Stratila. I think they're Romanian, so I apologize if I mispronounce their names. It says if we take a set E in the unit interval, which is a symmetric Kronecker set, and then we take a continuous measure supported on the Kronecker set, and then you take a measure-preserving system that is ergodic, and then you find some f in L2 such that the Fourier coefficients of your measure nu are given by the correlations of f, then f has a Gaussian distribution. In particular, f is going to be unbounded, and of course, the pointwise values of f cannot have norm 1. Yes?
I wonder how large is this collection of these Kronecker sets? For instance, what about finite sets?
So a finite set of points will be a Kronecker set if and only if they are rationally independent irrationals.
I see.
Yeah.
Okay.
And yeah, I haven't, I just checked this Kornfeld book and this Fourier analysis on Group's book by Rudin, and both of them, as far as making an infinite Kronecker set, they both just do the same construction of constructing a Cantor set based on, you know, you take finitely many points, and then you keep iterating, and you take a limit, and it makes a Cantor set. Yeah. Okay, so yeah, these are the main results for just representing positive definite functions. So I want to go into some more details about some of the proof techniques, and as I said, talk a little bit about the Gaussian measure space construction, and then, oh, sorry, I forgot. There are some, yeah, why not, these questions as well. So one thing that's missing, as I mentioned a few slides ago, is if our group G is just a general locally compact second countable group, then I don't know if we can still get this representation where the pointwise norm of the function is 1. Because my proof techniques very heavily use the fact that our group is abelian. I use Pontryagin duality. Yeah. And then another question that extends along this reasoning is if we take a positive definite function, and it's not just real valued, but it's also positive, then what special system and what special function f can we take to realize the correlations as to realize the values of the function as correlations of these functions on a measure preserving system? Again, maybe the naive answer based on what I showed you before is, oh, if the positive definite function is positive, then the function is positive, right? Because when it was real valued, you just make the function real valued, and when it was complex valued, you do the same for the function. Unfortunately, that is not true. There is this classical result known as Khinchin's recurrence theorem. And using Khinchin's recurrence theorem, we can say that if this function is a non-negative function, then these correlations are going to be bigger than some epsilon infinitely often. However, you can create a positive definite function that is decaying to zero. So Khinchin's recurrence theorem lets us verify that not all positive definite functions can be realized as correlations of a positive f. And then, of course, this begs the question of what are those positive definite functions that can be described as correlations for some non-negative f. And again, in section 4, it'll be very clear how this relates to a classical question of Ruja about distinguishing the notions of van der Corput sets and sets of recurrence. So there will be extra motivation for this later on. Okay. Now, what I was trying to tell you earlier, let's discuss some more details of the proof methods and the Gaussian measure space construction. So just very briefly, what is the Gaussian measure space construction? We take a locally compact second countable group, and then we take a continuous positive definite function, and this Gaussian measure space construction works equally well whether the positive definite function takes values in the real numbers or the complex numbers. So we can take our pick. And then we make a product space. We just take our field to the G. And of course, when you take a product space, the most natural thing to consider is the product sigma algebra. So we consider it. And we just take the right shift map. Right? So all of this is fairly standard stuff. And now all of the main content of the Gaussian measure space construction is black boxed in the next sentence. There exists some t-invariant probability measure, mu, which depends on the positive definite function, such that for pi e, which is the projection onto the identity coordinate, the values of our positive definite function are just given by these inner products, pi g with pi e. And of course, if you want to project onto the g coordinate, that's the same as projection onto the eth coordinate composed with this shift map, tg. So again, the content of the Gaussian measure space construction is in constructing this measure based on this positive definite function. And as you can see, or as is obvious in the name, it gives us a measure preserving system and a function whose correlations give us the values of our positive definite function. And it's called the Gaussian measure space construction because these projection maps have a Gaussian distribution. And then, of course, I'll just call this system that we make a Gaussian dynamical system.
So this is very similar to Gelfand member serial construction for countable groups. Is it just an analog, or you know about Gelfand member serial construction?
I remember Gelfand theory from functional analysis many years ago, but I don't know the specific construction you're referring to. I know people, yeah, can you elaborate on your question?
So it's almost the same, just for countable groups, you don't need measures there, but basically it's similar. Given a positive definite function, which is central, so function of conjugacy classes, you can realize it as a character of presentation by taking functions on your group and
and the difference is that this GMS gives you the Hilbert space. And here it's specifically L2. This is important for us to understand for this talk, right? That this is not an abstract Hilbert space.
I see.
Not a measure space.
Yeah, so I think this.
And in your concept, did you mention Gaussian? Because I didn't know.
No.
So this is also different.
But you see, in essentially here you just constructed measure, right? Not an abstract Hilbert space. So here Gaussian is again, well, this is the way you do it, right? So you could imagine you can do it differently, but there are no general instructions.
Yeah, so my understanding is indeed that the Gaussian shows up because it's useful for making the construction. The fact that when you take a sum of Gaussian variables, it's again a Gaussian variable that's used in the proof. As far as I know, it's not a benefit to know that the variable is Gaussian. Maybe other people know how to make use of this, but it's useful for making the system. And yeah, I think so other people have told me about this GNS construction. I think, as was said, it's about making a Hilbert space. So this is probably the same as the Gelfand Raikov that I had earlier. And I just called it Gelfand Raikov instead of GNS because in Templeman's book, Ergodic Theory of Group Actions, he attributes the result to Gelfand and Raikov, and I just decided to follow Templeman. But yeah. Okay, now the Gaussian measure space construction is very nice because it doesn't just give us a measure preserving system that relates to our positive definite function. It has special properties we can work with as well. So if we create a Gaussian dynamical system, then the following conditions are equivalent. The Gaussian system is ergodic. The Gaussian system is weakly mixing, and the Gaussian system is weakly mixing on the first chaos. The first chaos is the smallest T invariant subspace of L2 that contains pi e. So again, the reason that this is useful is this condition 3 really, right? This first chaos, this smallest T invariant subspace of L2 that contains pi e, this is completely determined by the positive definite function. So if you know your positive definite function, then you know everything that happens on the first chaos, and you can determine whether or not the first chaos is weakly mixing. So then you can determine whether or not your system is weak mixing or not even ergodic. All right, so this is again, a very useful property of the system. And while it's also, the next statement's not going to be relevant for the talk, but in case anyone cares about strong mixing, the Gaussian system will be strongly mixing if and only if it is strongly mixing on the first chaos. So it also has that nice property, just to further show that it's a good construction. However, the reason I went through the trouble of proving the first theorem for ergodic representations is specifically this equivalence between 1 and 2. So to see this in more detail, let's consider an example. We take our group to be Z because it's a nice simple group, and we can make a positive definite function by just saying phi of n is e to the 2 pi I n square root 2. And then we apply the Gaussian measure space construction, we get some measure preserving system, and we get some function, and the function satisfies Tn of f, inner product f, equals e to the 2 pi I n square root 2. And because this condition holds for all n, this is exactly saying that f is an eigenvector for t. Well, if f is an eigenvector for t, then the system is not weak mixing, right? One of the definitions of weak mixing is absence of eigenvectors. But then if the system is not weak mixing, it's not going to be ergodic. So this is a simple example in which we can apply the Gaussian measure space construction, but it will not produce something ergodic. More generally, we know that any compact group will only have finite dimensional representations, right? This is part of the Peter-Weil theorem. So you can never have a weak mixing action of a compact group. So if you ever apply the Gaussian measure space construction for a compact group, it will fail to be ergodic. But if your group is a weak mixing group, which by definition is a group that has no finite dimensional representations, then the Gaussian measure space construction is wonderful because your Gaussian system is going to be weak mixing, which is what you would expect. So what do we?
They also true that in this category you can prove mixing implies mixing of all overs, right?
I think that's still open. Well, that is still open. That seems reasonable, but I don't know, so I'm gonna hold off. I think if this is known, it's definitely stated in either Templeman's book or Glasner's book, because what you're saying does sound familiar. Now, what we have to do is focus on the exact situation where the Gaussian measure space construction fails, which is for compact groups, as I was just saying. So when we were working with Z, I had handled this myself in my thesis when I was trying to work with van der Corput sets. But of course, Z is pretty basic. I wanted to go beyond that. And I got stuck for locally compact second countable groups. And thankfully, I met Robin Tucker-Drob here in Warsaw a few months ago, and he helped me resolve this. And yeah, Robin claims that this should morally be well known because it's just a simple application of Peter-Weil. But I had asked several people before him, and they were unable to help me. So I don't know, the difficulty or ease of this result is for you to judge on your own. I'll give you a proof outline afterwards. So we take a positive definite function, and of course, I didn't write it here, but the group is still locally compact second countable, so as general as we want, and takes values in either the real numbers or the complexes. Now, we assume that this is a special positive definite function, because when we apply, we're assuming that when we apply Gelfand-Raikov to take a unitary representation of the group on a Hilbert space to realize the values as inner products, it's not just any unitary representation, it's a unitary representation that decomposes into a direct sum of finite dimensional representations, right? So this is what we would get if it was the action of a compact group, or if there was no weak mixing component. This is the exact situation where the Gaussian measure space construction fails. In this situation, there exists an ergodic measure preserving system and a function in L2 such that the values of our positive definite function is given by these correlations, Tg, F, comma, F. And as I promised, I'll just give you an outline of the proof. So what we do is we consider a group K, which is the closure of the image of G in the group of unitary operators on the Hilbert space. And our assumption that this representation decomposes into a direct sum of finite dimensional representations is exactly the assumption we need to ensure that K is a compact group, rather than just any old group. Now, our original positive definite function phi, we can extend it to a positive definite function on this group K, just using this density of the image of G. And of course, it's still going to take values in the same field. Now, I already told you K is compact, right? That's why we had, or that's how we made use of these assumptions, was to ensure that K is compact. Phi tilde is still going to be continuous, so no surprise that phi tilde is in L2 of K, right? Any bounded function on a compact group is going to be in L2, very basic fact. But why am I pointing this out? Well, we know that for any positive definite function that's in L2, we can realize it as inner products of the left regular representation. So this is a well-known fact. I don't know who to attribute this to. I just found it in Dixmier's C-star algebras, because as you know, it's a good book full of many facts. And then this is more or less the end of the proof, because now from this, I guess, a Koopman representation of K, we can more or less restrict it to a Koopman representation of G. And then we have the representation that we wanted. So modulo the mild details I checked, that's the proof. Then, of course, how do you put all of this together? I feel a little guilty because I did talk to Robin and I offered him to join me on this project, but we're working on other things together right now. So he basically helped me answer this question that I was asking 10 people. And then now that I have it, the rest of the result is very easy. So this is just restating the results from the second slide, right? That if we have a locally compact second countable group, then we can get an ergodic measure preserving system such that the values are given by these inner products. And again, just an outline of how we get this using what we've discussed so far. Gelfand Raikov, or as many people say, GMS, lets us get a unitary representation of G on the Hilbert space and the cyclic vector so that we can realize the values as inner products, right? At this point, we're still just on some abstract Hilbert space. We use a classical decomposition. We can always decompose our Hilbert space into two parts, one where the representation acts in a weakly mixing fashion, and one where it acts as a group rotation, or if you'd like, where it decomposes into finite dimensional representations. And then, of course, we decompose our function into two pieces based on this decomposition. Now, right, in the weak mixing part, we just apply the classical Gaussian measure space construction to make a weak mixing measure preserving system and realize the correlations from there. And in the compact case, we apply the theorem from the previous slide from Robin, and then we again realize these abstract inner products as inner products on a measure preserving system, which is ergodic. And then we know that a direct product of an ergodic system and a weak mixing system is still going to be ergodic. And the way you put your functions together is just this, what I've written here, right? Fairly straightforward. And you can check that the inner products of this is just going to be the sum of the inner products of the pieces. And we recover our original, we get the representation that we want on an ergodic system. Okay. So that's basically the story for this first result. Now for the other result on abelian groups, where we don't have ergodicity, but...
could you go back to slides, please? Thank you. So is it like obvious that you can take F to be real valued at this point?
Where? Like...
Okay, thank you. Oh, yes, I'm sorry, my brain caught up with me. Okay,
Yeah.
never mind. Sorry.
I mean, I can say a few words
No,
on it if you. Okay.
Thank you.
So now, yeah, there's this result of Ruja from 1984, which ultimately we're going to generalize this result and then use it to make our measure preserving system where the function has pointwise norm 1. So the result of Ruja is that if nu is a probability measure on the torus, right, we're back in the abelian case now, so I talk about probability measures on the dual rather than positive definite functions. Then there exists a sequence of complex numbers of modulus 1, such that the Fourier coefficients of this measure are given by Shizaro averages of correlations of the sequence with itself, and the Shizaro average of the original sequence is equal to the point mass at 0. Now, this exact statement does not appear in the work of Ruja. Ruja was studying van der Corput sets in this paper that I cited here. And because of the specific context in which he was working, he didn't need to formulate this statement. But it's very clear if you read his work, he was aware of this statement. This exact statement can be found, for example, in this survey of Bergelsen and Lessine, where they're simultaneously giving a survey about known results of van der Corput sets and generalizing these results from Z to ZD. And of course, they also explicitly say in their survey that they're modifying or following the footsteps of Ruja. So I think it's fair to say that this is Ruja's result. Now, we want to generalize this to countable abelian groups. And I want to make a slightly sharper statement. Again, for reasons that will maybe be obvious, well, that will be obvious when we get to section 4. So if we have a countable abelian group, I'm going to define S of G to be the subset of the unit circle that's the smallest set containing the image of every character in the dual group. And this is...
Is it otherwise known as the union of the images?
Yes. I don't know, is this a standard term? Union of the images of characters of the dual?
I think it's just a collection of sets. So usually we're just saying this is the smallest set which contains every set in your collection. So I think nobody would call it the union of the sets.
Okay. Yeah, we can call it that as well. Now, just to give a few examples to make sense of this definition, if our group is ZD for some D, then this S is just going to be the full unit circle. If we take a torsion group, say an infinite product of Z mod MZ, then S is just going to be the nth roots of unity. And then if we take this other torsion group, where rather than taking a product of the same group each time, we're changing the group that we take a product with at each step, then S is just going to give us all roots of unity. So now, if we have a countable abelian group and we have some Fulner sequence, then we can always take a Fulner subsequence such that for any probability measure on the dual group, there is a sequence of complex numbers, not just taking values in the unit circle, but taking values in SG, such that the Fourier coefficients of the measure is given by these Shizaro averages of correlations, and the point mass, not just at 0, but at any character, can just be calculated by taking a Shizaro average of the correlation with the complex conjugate of the character. So on one...
I know it probably is impossible to understand, but I have no idea what is a Fulner sequence. What is a Fulner sequence?
It's
difficult. It is difficult to explain.
No, it's
not.
fine. Right, in Z, we say that 1 to n, here, for example, wouldn't even need more. So the key property that we use here when we average by 1 over n, and n goes from 1 to n, is we're looking at these intervals 1 to n, and the reason we care about 1 to n instead of an arbitrary subset of integers of size n is that they're a Follner sequence. And what does that mean? It means that they're shift invariant. So if I fix some integer I, and I shift the interval by I, and I look at how much change there is, I plus the interval, and then remove the original interval, and I guess I should actually say size of this difference, and I divide it by the size of the original interval, then it goes to 0 in limit. So in the limit, we can't detect this shift. And then here, it just means that if I was to shift this Fn prime by some element, some fixed element of the countable abelian group, and then take a limit, then the shift would disappear. It wouldn't be detectable. So it's just the generalization of intervals to other groups.
What about the condition that the union is everything? Is this important?
For me, no. Yeah, that's. Yeah, it's an interesting question. I don't know if that makes any difference to this theorem on its own. Since, as I told you in the beginning, I'm just using this to construct a measure preserving system. So for the purposes of constructing a measure preserving system, any Follner sequence at all is good, which is why I don't even care about the fact that I had to take a subsequence. And then I, of course, also don't care about the fact that the union might not be the entire group. So this does also apply, for example, if in the integers you wanted to take sequences such as n squared to n squared plus n. Right, you could start with this as your Follner sequence in Z, and then you'll take some subsequence, and you can still apply this. Now, before I decide whether or not I want to do this, yeah, I think we have plenty of time, so I will give a brief outline of the proof here. So again, this is just repeating the statement from the previous slide.
So about your note, n squared plus n, so your Follner sequence does not need to be exhaustive? It does not need
Right. It does not need to be exhaustive.
I see.
Yes. So what we're going to do is we're going to take a sequence of monotilings of our group, and I should explain what that is. And in particular, we can monotile our abelian group using shapes that are Follner blocks. This is a result of Sechi and Cortez. So again, rather than give a formal definition, I'm just going to say what the picture is in Z, and I think that'll be more clear. So if we have G equals Z, then what we can do in Z is we can cover the integers using Follner blocks, right? So this would be like Right, we know that Z is such a simple group that the Fulner blocks are just intervals. Intervals are relatively shift invariant as long as you shift by something that's small compared to the size of the interval. So we can put intervals back to back and cover all of the integers. And then if we at some point decide that this interval is too small, it's not invariant enough with respect to what we're shifting by, we can just cover it again with a new tiling where we just take bigger intervals. And again, we can cover all of the integers with these bigger intervals as well. And then the story goes on. One day you decide you want to shift by something, 10 to the 10 to the 10, and this interval size is not big enough. So you can just keep covering your integers again using bigger and bigger intervals, right? No matter how much invariance you demand, you can pick an interval size big enough to satisfy your demand for invariance, and then you can cover all of the integers using these intervals. So it's a tiling because all of the integers are covered by translates of the same set, or rather it's a monotiling because all of the integers are covered by translates of the same set, and the shapes, right? These intervals are the shapes. They're Fulner blocks, right? They satisfy some level of invariance. So Sikhi and Cortez says that you can do this for any countable abelian group. And also maybe worth mentioning that Dovnarovich, Zhang, and Huchek showed that you can do this for any amenable group, but for an amenable group, they did not prove monotilings, they just proved tilings. So at each stage, you'll have a finite collection of shapes. So it's a little bit more complicated than abelian groups.
And this number is growing.
It could be growing, yes. Now, they do show that you can take the sequence of monotilings to have zero entropy, which in some moral sense, I think, controls the rate of growth of the number of shapes.
Monotiles or tiles? Other tiles, right? Because we have each step with a finite number. Why would you call that monotiles?
Sorry, I misspoke. For amenable groups, it's tilings with a finite number of shapes. It's still an open problem as to whether or not any amenable group can be monotiled using Fulner blocks. Yeah, so our first step is whatever our abelian group is, we take a nice sequence of tilings as we see here in Z. Now, I told you that I need to take a subsequence of the original sequence. So how do I do that? Well, I need it to grow sufficiently quickly. So, right, f prime k, or fk prime, should be at least, the size should be at least k cubed times the size of fk minus 1 prime times the size of the shape sk. So we just have some growth condition. And then it also needs to be sufficiently translate invariant, which is vague, but at step k, we might be translating by some different elements of the group. It's a fixed predetermined set, so we just need to make sure that with respect to those elements, we are sufficiently translation invariant. Now, what we do is, right, we have our tiling at step k, and we look at some tile, sk plus b, right? So it's like a shape, that's the sk, and then how much we translate it, that's the plus b. And we only look at the shapes that are contained in one of the Fulner blocks, but not the other, because we're inductively defining the sequence. So we're assuming that everything's been defined in here already, and now we're going on to the next block. And if we take some point in this block, right? So if we have the points here would be like, we look at the points in here, then we can define the complex numbers. We can define these CGs in the following fashion. We take random variables, right? These XDs are random variables. They're independent, identically distributed, taking values in the dual group with distribution given by nu. And then we can say that CG is G hat of XD. So this would mean when we look at the block, we write out what the points in the block are relative to this center. And then if I want to know the complex number here, C sub 1 plus D 2 comma 2, then I take the 1, I can view it as a character on the dual, or in the double dual. This is why I need abelian to say that G is isomorphic to its double dual. And then I can evaluate it at a random variable indexed here. And of course, if you just use the definition of double dual, you can unpack it like this. So this is definitely going to be a complex number, not just of norm 1, but a complex number generated by some character on the dual group, which is why we could take values in S of G rather than just the unit circle. And the reason this works, the purpose of this construction, is that this random variable, this xd22, it's the same on this entire block, right? If you change blocks, then you change random variables, but as long as you're in the same block, the random variable is the same. And that's useful because if we look at, I guess, do you want to? No, that looks pretty similar. So if we start looking at these correlations, then the correlation for G in this block, F2 plus D2 comma 2, it's basically the same as the correlation for the G's that are here, right? Because we're translation invariant, we can ignore whatever small piece we lost. So then on here, everything is defined using the same random variable. So we can just use the algebra of the group and say that this is going to be equal to right? These random variables being the same means that we can just cancel out the G's and get this, H. And that's what we wanted, because now that these are just random variables all being input into the same function, when we take the Shazaro average, you apply the strong law of large numbers, or in my case, Hosting's inequality, because I need to control the rate. And this will converge to the integral of the function, which is going to be the Fourier coefficient that we're after. And then the story for the second half of the equation is similar, but I won't go into details there, because I think this gives enough of the idea about why we need these Fulner blocks and these tilings. So that we can, the Fulner blocks allow us to actually make use of the algebra of the group, cancel things out, and then just apply Hosting's inequality.
Sorry, I miss, so in this proof, when you take fk prime, do you require that the tiles of the form sk plus d cover sufficiently large portion of the difference?
Right, that's the reason that I had this assumption, is that this fk prime is so much bigger than k minus 1 prime that when you just fill in the difference using these tiles, you're filling in a large percentage of the difference so that whatever happened before is negligible.
So this is automatic just from the comparison of the sizes?
Yeah, it's automatic from this growth condition.
I see.
Yes.
And is there a hope to generalize this result for, in some sense, for non-abelian groups?
So, as I mentioned, these tilings, we have the tilings for amenable groups. Now, they might not be monotilings, but actually that's not a problem. To be honest with you, when I first uploaded this to archive, I was not aware of the paper of Sikhi and Cortez, so I just cited the Dovnarovich, Huchek, and Zhang paper, and I just did the same proof using tilings that have finitely many shapes at each step, and it works. It's just more annoying. There's more details to keep track of. So that part's fine. If you go to an amenable group and you have tilings that use a finite number of shapes, that's not a problem. The problem for me is that we don't have Pontryagin duality. So this step, where I say the group is isomorphic to the double dual, fails, and that makes some problems. So you can, the problem is when you study a general amenable group, or really anything beyond an abelian group, you're going to need to consider representations of the group that are not just one-dimensional. They'll be 2, 3, even infinite dimensional. And then it's not yet clear to me how to extract a complex number of norm 1 from, say, an infinite dimensional representation. So I hope something here can be extended to the setting of amenable groups, but I have not been successful in doing it.
You can ask one question because it's not clear to me just from the syntax. So your xd are IID variables with values in g hat.
Yes.
So you evaluate them at g.
Yes.
And do you then integrate it with respect to mu? I don't understand this line cg plus d is equal to g hat of xd. Because then cg plus d would still be random, right?
Yes. Oh, so the last thing I should say here is that this construction almost surely produces a sequence that satisfies these conditions. So that's a good point.
But you just say that almost surely it will be okay.
Yes, almost surely it will be okay. That's right. Okay. Now,
so that's probably another reason why you want your group to be countable, right? Because
I want a countable Fulner sequence, which any second countable group will still have a countable Fulner sequence. But do I actually? Oh no, no, I think you're right. It's not just the Fulner sequence that has to be countable, but the number of translates should also be countable. So yes, I do want my group to be countable for this one. Yes. Now, I was gonna give you an outline of the proof here. How this is the statement of a restatement of the results from the second or third slide, where we make the measure preserving system and the function whose norm is 1. Actually, I have until 45, right?
Yes.
Okay, why not? I can spend a couple minutes here. So, using the theorem from the previous slide, we take our sequence of complex numbers of norm 1, or if you like taking values in S of G, and then take some Fulner sequence such that these correlations give us the Fourier coefficients and the point mass at 0. Now we take the stone check compactification. Just for my curiosity, can I get a raise of hands? How many people are comfortable with the stone check compactification? Okay. Okay, that's a good percentage of the audience. I'm quite happy with that.
You were supposed to raise your hand.
Okay. So one of the defining properties of the stone check compactification is that if we have any bounded function on our group, then there's a unique continuous extension of that function to the entire stone check compactification, and the values are gonna still be bounded. They're gonna take values in the closure of the original, which is maybe obvious from the fact that it's continuous. So we take this unique continuous extension of the sequence we constructed, where we now view the sequence as a function instead of a sequence. And then we take this natural action of the group on the stone check compactification given by left translation. This is not just going to be measurable, it'll actually be continuous. Then we can, given the Fulner sequence, we can use it to construct a mean on the group, a mean on the group G. This step would also work for any amenable group, right? I'm using the fact that abelian groups are amenable and I'm making a mean. And then the mean is not the same thing as a measure, but a mean on the group lifts to a measure and tilde on the stone check compactification. And then that's basically the proof, right? If we look at TG of C tilde inner product C tilde with respect to this measure, we're going to recover the Fourier coefficients, right? This inner product here, if you unpack the definition, it's going to exactly be this limit, and then we're just going to get the Fourier coefficient. And
so you do not get ergodicity here because there's no way of knowing if the lift is ergodic, or is there some other reason which I'm not seeing?
So in general, okay, so this will not be ergodic for sure.
Yeah.
Because so the way you construct the mean on the group is you say that for any set A, you take the size of A intersected Fn divided by the size of Fn, and then P, you take any non-principal ultrafilter, and then you take a P limit. Right? This just ensures that the limit exists. It automatically does your diagonalization arguments for you to make sure that these limits exist. And then this is just going to be a mean. Now, for example, if we go back to Z, just because the geometry is simpler, this is a Fulner sequence, right? It's going to be more and more shift invariant because it's just some intervals of length 2n. So I can define the mean in this fashion. So if I say A is equal to the union of n cubed plus n, right? This is clearly half of our space, but again, because of translation invariance, the shift by I is not detected. So this is an invariant set of measure. Well, when you lift it to the Stonecheck compactification, then it's an invariant set of measure 1/2. So it is not going to be ergodic. You're welcome. Thank you for the question. I guess that was an important question because I was kind of wishy-washy about the lack of ergodicity in the beginning, but it is very clear from this particular construction that it will never be ergodic. Okay, so that was all of the general abstract business about positive definite sequences, and now I want to show you how this relates to van der Corput sets and sets of recurrence. Of course, I have to begin by telling you what is a van der Corput set, and then next slide, what is a set of recurrence. And I'm somewhat cheating here. This is not the original definition of van der Corput set. It's a theorem from this paper that the definition I'm showing you here is equivalent to the original definition. But due to time constraints, I just wanted to give you the definition that or the characterization that directly relates to positive definite sequences, unitary operators, and everything we've been discussing so far. So for our purposes, a set of natural numbers is a van der Corput set if for any unitary operator on the Hilbert space, any vector in the Hilbert space satisfying that UVF inner product F is 0 for all D in V, we have that the projection onto the space of U fixed points is 0. Okay. Now, the following are equivalent to being a van der Corput set based on the results I showed you from, I guess, slide 3. So for any ergodic measure preserving system and any function f in L2 satisfying that TBF inner product f is 0 for all v and v, we have that the integral of f is 0. This uses the ergodic characterization or ergodic representation for positive definite sequences. And then this is equivalent to saying we now take any measure preserving system, it doesn't have to be ergodic, but now we only look at functions f whose norm at each point is 1. And then if the inner product of these is 0, right, if TVF inner product f is 0 for all v and v, we again have that integral of f is 0. And then we can repeat either of the previous two characterizations, and rather than looking at all f in L2, we just look at all real valued f in L2, or in this case, all real valued bounded f in L2. Okay, now again, there is a long list of characterizations of van der Corput sets, many more than what I'm showing you here, but I'm almost at the promised punchline of the relationship between van der Corput sets and sets of recurrence. So I hand-picked characterizations that are related to this purpose and ignored all of the other known characterizations. Now, what is a set of measurable recurrence? A set of integers is a set of measurable recurrence, and this is the honest-to-goodness definition, no cheating this time like I did last time. If for any measure-preserving system and any set of positive measure, there is some R such that the measure of A intersect TRA is bigger than 0, right? Sets of recurrence are those sets for which you can witness Poincaré's recurrence theorem happening along that set. And of course, you can make many characterizations for these as well. Rather than taking sets of positive measure, we can take our measure preserving system, take a function f that's non-negative, and I don't want the 0 function, right? So non-negative and not identically zero, or not almost everywhere zero. For any such function, there should exist a R such that inner product of TR f with f is bigger than or equal to 0. This is, if you're bored, you can take it as an exercise to show that this is equivalent to the definition. It's not too difficult. Second characterization is that if you're a set of recurrence for all ergodic systems, then you're also just a set of recurrence. That's an exercise using the ergodic decomposition. So it uses some heavy machinery, but if you use it, then not too much more difficult. And then, of course, same story is that I can repeat one and just say that require that it holds for all ergodic systems. And then this fourth one seems a little different. For any sequence xn taking values in 0 and 1, if the sorry, that's definitely a typo. Let's say Cn here, because I put Cn there.
Thank you.
Yes. Sorry about that. If all of these correlations of Cn plus R with Cn are 0 for all R and R, then we must have had 0 density of 1s in our sequence Cn. So this might seem a bit unrelated at first to the previous characterizations, but given our discussions about the Stonechek compactification, shouldn't be too surprising that from these sequences we can make a measure preserving system and identify the sequence with a set of measure being equal to what we have here. Now, again, we can see, for example, here, characterization 1, if I said any real valued f that's not 0, I would get the characterization of van der Corput sets from the previous slide. Real valued bounded f that's not 0. I would get van der Corput sets. But if I take positive valued bounded f, then I get set of recurrence. And same thing here for ergodic systems. If I have an ergodic system and I take all real valued non-zero f, I get van der Corput set. If the system is ergodic and I take all positive valued f, I get set of recurrence. Right, so this difference between sets of recurrence and van der Corput sets seems to be very small. It is precisely the difference between considering real valued functions and positive valued functions, or I guess non-negative valued functions in these correlations. So is there actually a difference? Well, this has already been investigated. Kamei and Mendes France introduced the notion of van der Corput set, and they showed that every van der Corput set is a set of recurrence, which is obvious to us given the characterizations that I showed you, but again, given the original definition, it was not obvious, so that's why it was a genuine result of theirs to show this. Ruja is the one who actually named this notion van der Corput set, and he asked if every set of recurrence is a van der Corput set. Then it was a very difficult result of Bourgain to construct an example of a set of recurrence that is not a van der Corput set. So it's not only me that thinks this result is very difficult. I read the paper, formally verified every line is true, and have no idea what he did. Well, to be fair though, the first 2 sections of the paper are very readable, very nice. The third section where he proves the main result is where I have no idea what he did. I just know that it's correct. I also, I won't name names, but I know some people who are very established and also claim that they read the paper and don't have any intuition.
But I don't think it's the only paper who such a claim is being floated. He has very hard papers.
I have heard this as well. Yeah. Now, there is this guy, Andreas Muntakis, who's a student of Joel Moreira, and he has a refinement of Bourgain's construction. To be honest, I have not yet read Muntakis' paper. It's been on my to-read list for a long time. I'm hoping it's going to be easier to understand. I'm pretty sure it's not going to be harder to understand. But yeah, so Muntakis has modified Bourgain's construction, so we have at least one person who knows what's going on. But all of this to say that it's very difficult to show that there exists a set of recurrence which is not a van der Corput set, and I think it's fair to say that it is still in general not well understood what is the difference between a set of recurrence and a van der Corput set. And there's still some interest in this amongst people like Muntakis and Joel Moreira. So of course, just to restate the questions from earlier, I was asking those questions because I want to better understand what is the difference between a van der Corput set and a set of recurrence. So I'm just repeating those questions. And you know, all of the discussion of the last couple slides was for the integers. We can play this game of set of recurrence and van der Corput set for more general groups as well, which is why I formulated these questions more generally. So again, to repeat myself, if we have a positive definite function, could either be on Z or just on a abelian group or locally compact second countable, whatever generality that you like. It's real valued and non-negative. What functions can we pick so that the values are realized as inner products? And again, if we have a positive definite sequence whose values are realized by inner products of a non-negative function, well, what subclass of positive definite sequences does that give us? Right? So understanding question B is one way of understanding the difference between van der Corput sets and sets of recurrence. And while question A is not going to be as useful for this purpose, I think it's a natural question to ask, given that the answer is not just the trivial answer of, oh, if this is positive, then this should be positive, right?
Did Rosa have an application in mind when asking this? So in some sense, is it better when you know that the set is van der Corput? Is it easier? Why would you like this characterization?
So to be honest, as much as I like van der Corput sets, I'm still not aware of any applications of them. I believe the argument is that recurrence is a topic in which there's a lot of interest. So then, of course, sets of recurrence are a topic of interest. And then, because van der Corput sets are intimately related to sets of recurrence, they are a topic of interest. But unfortunately, I have yet to see a paper where they said, oh, we wanted to apply van der Corput's difference theorem, but we couldn't check all the values, so we just checked along some van der Corput set and it worked out and did what we wanted, and we solved this other person's problem. I have not yet witnessed such a thing, but I have my fingers crossed that one day either I will write that paper or someone else will write it for me. Yeah. I'm sorry, not the most satisfying answer, but I just have to be honest. Well, I guess the only other thing I maybe can say is one of the equivalent characterizations of van der Corput sets that connects it to harmonic analysis, and I suppose is more interesting. I can give you that and hope that it provides some more interest. So I guess in harmonic analysis, people care about understanding how smooth a measure is based on its Fourier coefficients. That seems to be a central topic of interest. So van der Corput sets relate to that because one of the equivalent characterizations is that your set of integers is a van der Corput set if the only measures whose Fourier coefficients vanish on the van der Corput set are those that have no point mass at 0. And this is actually the same as saying mu is continuous. You can consider rotations or translations of your measure. So if there's no point mass at 0, under this condition, there's not going to be any point masses anywhere else. So there is, I guess, maybe some hope that it'll be of interest to harmonic analysts. Okay. Let's see, oh, good, okay. So I can still say a few more things that I wanted to say. Now, I think I'm gonna skip this one this time, because I wanna, yeah. So now there's this other notion, a set of nice recurrence. A set of integers is a set of nice recurrence. If for any measure preserving system and any epsilon bigger than 0, there's an R for which the measure of A intersect TRA is close to mu A squared. Or I guess not close to, it's just a lower bound. But this is mu A squared because there's this thing called Khinchin's recurrence theorem, which says if I took the average of these expressions for all integers R, all natural numbers R, the average would be bigger than equal to mu A squared. So there have to be some R's for which the individual intersections are bigger than mu A squared minus epsilon. And a set of nice recurrence will always have at least one of those R's in it. We know that there is a set of recurrence that is not a set of nice recurrence. This is a strictly stronger notion. Then, similar to nice recurrence, we can make a nice van der Corput set. I guess I could have reformulated this with unitary operators, but I didn't think ahead and just went back to the original definition of nice van der Corput set from Bergelsen and Lessine. A set of integers V is a nice van der Corput set if for any Cn, complex number Cn of norm 1, we have that the lim sup of these correlations, or I guess the supremum over V of the lim sup of these correlations, Cn plus V times Cn, is bigger than or equal to the square of the traditional Shazaro average of the complex numbers. So again, if we just took the sup over all integers V, then this would be a result of some sort of a Cauchy-Schwarz. So there is going to exist some V, and a nice van der Corput set is just a set for which you always have at least one of those V's. And now I guess it's good that I actually wrote this definition because the third definition relates to that. A nice FC plus set, right? FC means forces continuity, right? We forced the continuity of this measure. A nice FC plus set means that for any probability measure mu on the torus, the supremum of the absolute value of the Fourier coefficients along this set is at least the size of the point mass at 0. Okay, well, what do we have? So, yeah. I guess what I said here is that if I omit the word nice here and I omit the word nice here, then the notions are the same. Van der Corput set is the same as a forces continuity set, which is what we have here. And I already told you that if I omit the word nice here and I omit the word nice here, then VDC implies recurrence, and recurrence does not imply VDC. That was the whole Rouget-Bourgain story. So what do we know in the nice situation? Well, Bergelsen and Lessine showed that every nice FC plus set is a nice van der Corput set, and it's also a set of nice recurrence. And then in the other direction, they showed that if V is a nice van der Corput set, and nu is a probability measure on T, then the supremum is going to be at least the point mass squared. So it's kind of sort of almost a nice FC plus set, but it's not actually a nice FC plus set. Or at least it's not yet proven to be an FC plus set. So this characterization is more difficult to prove in the nice situation. In fact, it's still an open problem. Now, I did show that every nice van der Corput set is a set of nice recurrence in my PhD thesis. This was an open problem from the Bergelsen-Lessine survey. And then I didn't show that every nice van der Corput set is a nice FC plus set, but I showed something similar. So F, the set of integers F, is a nice FC plus set if and only if, for any sequence of complex numbers, this time the complex numbers are not of norm 1, it's more general. Any sequence of complex numbers such that this Shazaro average is finite. So it's definitely satisfied if they are of norm 1, but it's a much larger class in general. If for any such collection of complex numbers, we have that the supremum of the lim sup of the correlations is bigger than or equal to the square of the Shazaro average, this is an alternate characterization of FC plus set.
Right. So there need limit when goes to video or lim sup something.
Lim sup here would be better, yes. So that's another small typo. Thank you for catching that. So, okay, why can I prove this? Well, if we go back to the beginning of this presentation, if I allow my, if I want an ergodic representation of a positive definite sequence, I can't guarantee that the function I get is going to be bounded. So in order to make this happen, I have a proof that uses the pointwise ergodic theorem. And to cleanly use the pointwise ergodic theorem, I want ergodicity of my system, which means that I need to allow for functions that are unbounded, which translates into allowing for complex sequences of complex numbers that are unbounded, but satisfy this L2 condition. So that's why I can almost answer their question and show that a nice van der Corput set is a nice FC plus set. But again, right, they defined it with complex numbers of norm exactly 1, and my proof does not work in that situation, because if I take a representation where the functions have pointwise value exactly equal to 1, I lose ergodicity. And as we saw with the Foias Stratila result, I can't just improve my proof to take a simultaneously ergodic system and the function with pointwise norms 1. Something more refined needs to happen. So this hopefully shows you why I was interested in these problems, because they do relate to this open problem of Bergelsen-Lessine about nice van der Corput sets, nice FC plus sets, so on and so forth. So of course, it's still open as to whether or not every set of nice recurrence is also a nice van der Corput set. We have not yet managed to modify Bourgain's proof or the recent result of Muntakis to answer this question. As I just told you on the last slide, we still don't know if every nice van der Corput set is also a nice forces continuity plus set, because of this issue between ergodicity and boundedness of our function in the representation. And we also don't know, for example, if there's any relationship between the class of sets of nice recurrence and the class of van der Corput sets. Right? We know that both of these notions are nice recurrence and van der Corput set are strictly stronger than set of recurrence, but we don't know how they relate to each other. And then the last question, so I put this as a question because it can possibly help us understand whether every nice van der Corput set is also a nice forces continuity plus set. Again, keeping in mind this is based on the result of Foias and Stratila. I apologize for butchering their names. If we take a symmetric Kronecker subset of the 0-1 interval, and we take a probability measure that's supported on the set, what can we say about the places where the Fourier coefficients vanish? So if we can understand this, then I think it could shed some light on whether or not every nice van der Corput set is a nice forces continuity plus set. So that is everything I had prepared for today. And that's the end of my presentation. Thank you for your attention.
Are there any further questions? We had a lot of questions during the talk, so.
You did, and for that I'm very grateful.
I'm sorry.
I don't know, do we have people online?
Yes. I think they have questions.
Oh yeah, I'm sorry I wasn't checking the chat for questions. Although I guess I prefer not to do that.
They're all false for not from a flag in here.
Yeah.
So I just checked for you and this small tail in the S. It's like SZ in Polish. It's a sh.
So Foias,
Foias.
Foias.
Ah,
Oh, okay. Sorry, I thought they were French.
okay, so let's see. Thanks.
Thank you. Goodbye.
Thank you. Bye bye.
Bye.
Thank you. Bye.
Bye.
Yeah, I think that's might mean he went to the doctor or something. But I didn't want to cry. Very nice talk. Thank you. I'm sorry for my stupid questions because I just have no idea about the sequences.